Hi class, welcome to exercise 10F, division of polynomials. And in your lesson today, we only got the one example, which is example 12, dividing polynomials. And your pre-learning for this example is questions 1, 2 and 3 in the new book, and questions 3 and 4 in the old book. So even though we've only got the one example there, this is a super important but challenging topic. And if you nail it, the rest of this block will be fairly easy. But it also could be a nightmare if you don't nail it. It's a very challenging topic, and that's based on my experience teaching this for quite a few years. So because of this, we've got a two-part introduction, and the building understanding questions are at the end of part 1. So don't expect to master this topic without going through those introductions carefully. Alright, we'll see you in part 1. As I said, this is traditionally a very hard topic, but it shouldn't be if we reimagine division. So let's start that with some numbers. Now, I don't know about you, but I've always seen A divided by B as having A amount of things and B bags, and then moving A things into the bags and evenly splitting them among the bags. And then the answer to the division is how much is in each bag. So I know that's not numbers, it's letters, but let me use a number example, alright? So let's start off with 9 divided by 3. So I'll draw 9 things and 3 bags. Then I can drag 1 across to each bag, and we've still got some more, so another 1 to each bag. And I started to get ahead of myself, but yes, of course we keep going. We can see that inside each one of those bags, there is 3. So that means that 9 divided by 3 is equal to 3. And if we were to try something like 8 divided by 3, then we've got 8 things and 3 bags. And once again, I can drag 1 thing into each bag and a second thing to each bag. And we've still got 2 left over here. And there's no way that I can split that evenly among the 3 bags. So that means that 8 divided by 3 is equal to 2 plus 2 remainder. And these 2 remaining, we could break up into thirds each and then split them evenly. So that would mean that 8 divided by 3 is equal to 2 plus 2 thirds. And the terms for all these things here are that 8 is the dividend, i.e. the thing that's divided, and 3 is the divisor, the thing that is dividing, and quotient is the biggest whole number division of it, and of course 2 is the remainder. Now there's another way of looking at that too. So division is the opposite of multiplication. So if I multiply both sides by 3, we could also say that 8 is equal to 2 times 3 plus 2. Now just using these very simple examples, I think I've demonstrated how I think about division, and I also suspect that that's how most people think about it. But there is another way that's dumb enough even for a computer. So if we're thinking back to A divided by B, I've got my A things, trying to fit them into B bags. But each time I distribute 1 to each bag, I'm actually subtracting B away from the pile, i.e. the pile A minus B. So once again, let's have another simple number example. So if I got 11 things and I'm trying to fit them into 3 bags, so instead of counting off 1, 2, 3, I can count off 3. And then for the next lot for each bag, I count off another 3. And then I count off another 3. But we've still got these 2 left over here. And there's no way that you could distribute them evenly among the bags. So we have to stop there. So what we've done here is we've started with 11, subtracted 3, and that's 8. So 8 take away 3 is equal to 5. And then 5 take away 3 is equal to 2. Then the first number less than 3, we stop. And of course 0 is nice because that means we've got a perfect divisor. But anyhow, we'll talk about that later. So that means that 11 divided by 3 is equal to 3 in each group and 2 left over. So we're repeatedly subtracting the divisor from the dividend until you have a number that is less than the divisor, and this number is the remainder. Then the number of times that the divisor was subtracted from the dividend is the quotient. So I hope you can recognize that this is just like putting things evenly into a bag. We're just counting the whole lot in one step. Now I've got this spreadsheet here that I'd like to show you exactly how a computer would do this with much bigger numbers. All right, let's look at this spreadsheet. I'll post a copy of this on the OneNote for this lesson, so you can use it anytime you want. Please note that there's a limit to the size of the quotient, but we'll see more about that later. And all you need to do is enter the dividend here and the divisor. And what I set up is that it will just continually subtract. And this is exactly what a computer would do. And as soon as it hits a number in this column that's less than 3, then it stops. And it counts the amount of times that it's done the subtraction. And there we've got our quotient. So let's have a look at a bit better number than 11 divided by 3, which we can do by hand. Let's try this. 2588 divided by 9. So 2588 divided by 9 is equal to 287 with a remainder of 5. And if you were to put that in decimals, 5 divided by 9 is 0.55, lots of 5s there. Okay, and you can see the calculator says the same thing, 287.55, and so on. Okay, so what happens here is we start with our 2588, as you can see, and then you subtract 9, we get 2579, and on it goes. And the reason why there's a limit to the quotient, you'll see as I scroll, you can see we're continually counting here, and we get to the end, 285, 286, 287, and then that number is less than 9. And you can see it here, so 23, take away 9 is 14, take away 9 is 5, stop. So as a little hint to what we're going to do later on, I personally wouldn't want to count 287 subtractions. So you might look at, say, take away 100 subtractions, if I can just scroll up. So once we've taken away 100 subtractions, we've got 1688, which is 2588 minus 900. Now let me change this divisor to 4, and you can see we've got a remainder of 0. So 4 is obviously a factor of 2588, and the quotient for that is 647. And if we scroll down to the end there, you can see we go 840. So that's the first number we came across that's less than 4. Of course, we can do bigger numbers like 232456. And whoa, you can see that it's saying it's 867 as well. Well, that doesn't make sense, does it? But have a look at the remainder. Okay, so 867 times 4, when that's subtracted from this big number here, we're left with this much of a remainder. Looks like my quotient maximum is 867 here. Obviously I saved a copy another time that had a quotient this big, but if anyone who knows how to use a spreadsheet, you can copy these formulas and drag them down. Anyhow, if I pick a bigger divisor, you can see the quotient is 50 now. So 50 times this divisor, when I subtract that away from this, we'll be left with 3,306, which is obviously the first number less than 4,583. And if I was to pick another dividend that's less than the divisor, you can see the quotient is 0. So we're automatically into fractions. All right, let's go back to OneNote. All right, now that we're back here in OneNote, I'm going to drag in a copy of that file. Okay, and that's named division is subtraction. And you can use that yourself to try out anything you'd like. All right, so as we saw, this is not a complicated method. It's just got many repeated simple steps, which is perfect for a computer. But one thing I take away from it is that it's really nice to know that division can be simplified to repeated steps, just like multiplication can. So any of you know how to write a while loop in a computer? There you go. That's how you can do division. But by hand, it's going to take a long time. So my question is, do you think that we can shorten this? What do you think? I did give away a clue in the spreadsheet part of the video. Well, the answer is yes, we can. The way we shorten the work for us by hand is to take grouped subtractions. So let's do a bigger number like 3,285 divided by 7. Now, the way it was going in the machine was saying 3285 take away 7 would be 3278, which is step 1. So at this stage, our quote-unquote remainder is not less than 7. So do another one. So we've got 3278. Take 7 from that, we have 3271, and that's step 2. So for each step here, by the way, what we're saying here is that 3285 minus 1 times 7 is equal to 3278. And 3285 take away 2 times 7 is equal to 3271. Okay, and that's going to help us with how we set it up later on. But I'm not going to keep going like this. This is something you definitely should leave for a machine. Okay, we're people. We're going to come up with a smart shortcut. Okay, so let's start off. 3285 divided by 7 looks like this when I write it in the long division term. So I'm going to try and find multiples of 7 that fit into 3285. So 7 times 1,000 is obviously bigger than that. 7 times 100 is 700, but 7 fours is 28 and 7 fives is 35. So if I say 400 times 7, then that's equal to 2,800. So if I subtract that away, we've now got a remainder of 5, 8, and 4. So 485. And I'm going to put the 400 I just wrote down up here. All right, let's look for multiples of 7 that go into 480. So we can use multiples of 10 here. 7 times 6 is 42. So 7 times 60 is 420. So I'm going to put my 60 up the top here and then subtract away the 7 times 60 here. Now I'm going to need a single digit here. So we've got less than 70. So we've got 9 sevens are 63. So I'm going to put my 9 up the top and subtract away the 63. We're left with 2. And because that's less than 7, we should stop right there. And because 400 plus 60 plus 9 is equal to 469, then you traditionally write that as 3,285 divided by 7 equals 469 plus 2 sevenths. So we have shown actually that 3,285 is equal to 469 times 7 plus 2. So I'd like to make a little note here about what we're actually saying. Well, we started off with 3,285 and then we subtracted 400 times 7 and then we subtracted 60 times 7 and then we subtracted 9 times 7 and that was equal to 2, and we stopped there because it's smaller than 7. So obviously 7 is a common factor with those 3 brackets there, and 400 plus 60 plus 9 is 469. So what we really got is 3,285 minus 469 times 7 is equal to 2. And then if I add this subtraction to both sides, we've got 3,285 is equal to 469 times 7 plus 2. So if we were to divide both sides by 7, we get 3,285 divided by 7 is equal to 469 plus 2 divided by 7. But for what we're going to do in this unit, we really want you to express it this way. But it is a division, okay? So I just want to make one more note because I really want to ram home how important it is to get that remainder concept right. So 469 had to be the quotient because 3,285 minus 470 times 7 is equal to minus 5. So this means we've got a negative remainder. So we've gone too far. So it's definitely not 470 as the quotient. If we did 3,285 and subtracted 468 times 7, we'd be left with 9. And that is not less than 7. And don't forget, 7 is also not less than 7. So that means that the Goldilocks remainder must be one of 0, 1, 2, 3, 4, 5, or 6 when we're talking about 7. Because if I land on 7, then 7 subtract 7 is 0. If I land on a number bigger than 7, then it's going to be more than 0. And if I land on one of these numbers you can see written down here, if I subtract 7, we're going to be at a negative number. So what you need to do is get to the smallest possible non-negative number. Alright, so this is the end of part 1 of the introduction. So please pause the video now and do the building understanding questions in the new book or questions 1 and 2 in the old book. Okay, long division is something you don't spend a lot of time on normally, because I believe with numbers it's silly. You can just use a calculator. But it's not so easy to just use a calculator when it comes to algebra, and that's where we're going to take it in the next part of the introduction. See you there. So how'd you go? Are you now confident making grouped subtractions to supplement division? Hopefully you are, because the same principles are going to apply for polynomials. So for example, if I had this polynomial x cubed minus x squared plus x minus 1 divided by x plus 2, then it's going to equal some quotient polynomial plus a remainder, which is divided by x plus 2. And the way that we're going to find this quotient is by subtracting multiples of the divisor from the dividend. And it's important to note that we are focusing on removing the terms that have an x in it. And in the end, we just aim for a number in the remainder. So looking at that polynomial, it's x cubed minus x squared plus x minus 1. And then putting in the long division form to divide it by x plus 2. I can now start looking at multiples of x plus 2. So the first term there is an x cubed, and the first term in my divisor is an x. So then I'm going to multiply x plus 2 by x squared. And I'm going to put my x squared up the top here. And of course this x squared helps me remove the x cubed. So x squared times x plus 2 is x cubed plus 2x squared. So when I subtract that away, we obviously get rid of the x cubed and we're left with minus 3x squared plus x minus 1. Okay, so now I've got a leading term of minus 3x squared. So if I choose minus 3x and multiply that by x plus 2, then we get minus 3x squared minus 6x. And that's why we chose the 3x, because we wanted to remove the minus 3x squared. Alright, so of course we're going to subtract that away, and that will give us 7x minus 1. So I've got another x there, so I want to multiply our x in our divisor by 7. So 7 times x plus 2 is 7x plus 14. And of course we chose that to help remove the 7. Now I need to put the 7 up the top here, by the way. Don't forget that. And now when we subtract away our 7x plus 14, we get minus 15. Okay, 7x minus 7x is 0. 1 minus positive 14 gives me minus 15. So that means that minus 15 is our remainder, because we've got no x terms left. So there's no multiple of this linear thing with x that equals minus 15 for all x's. So this is where we stop with the polynomial long division compared to the numbers. Now you might want to express this as x cubed minus x squared plus x minus 1 divided by x plus 2 is equal to x squared minus 3x plus 7 minus 15 on x plus 2. But it's better to write it out with x cubed minus x squared plus x minus 1 equals x plus 2 times x squared minus 3x plus 7 minus 15. And in this form we say we've got the dividend is equal to the divisor times the quotient plus the remainder. And also, as I showed with the numbers, what we're really saying is that we started off with our x cubed minus x squared plus x minus 1. Then in the first step, you noticed we subtracted x cubed plus 2x squared. And in the next step, we subtracted minus 3x minus 6. Sorry, that was minus 3x squared. And then we finally subtracted 7x plus 14. And that left us with a remainder of minus 15. But if I can rewrite that with the polynomial at the front. But for each one of these brackets, I can take out the common factor. So we've got x squared in both of these things. So we've got minus x squared times x plus 2. And I made a mistake in the last line. That should have been 6x. Right, so we've got a common factor of minus 3x in these ones. And that leaves us with x plus 2. And if I take out the common factor of 7, we've got 7 times x plus 2. And that was still equal to minus 15. So working backwards with the distribution law you used in the last lesson, you can see now all of these terms times x plus 2. So we can see we've got a minus x squared and a minus 3x and a minus 7, so minus plus 7. And they were all multiplied by x plus 2. And that of course is still equal to minus 15. So if I add this product to both sides, we're left with x cubed minus x squared plus x minus 1 is equal to x plus 2 times x squared minus 3x plus 7 minus 15. Alright, so let's go back and have a look at it one more time. So we've got our x plus 2 and we're trying to divide it into this blue polynomial. So what times x gives me x cubed? Well, x squared does. So I've got x squared times this x plus 2 and I've put it there and subtracted it away. So I'm storing my x squared up here. And again, I try and get rid of the minus 3x squared. So I choose 3x because that's multiplied by x to get minus 3x squared. And I do the same thing with the 7x. And then finally, we're left with the remainder of 15. All right, let's get on to the next section where we'll do another one of these examples. Okay, I don't expect you to actually get this without watching both parts of the introduction and doing the building understanding section. All right, so I'm going to explain this formally and then do a couple more examples. So what we're going to say is, when seeking a linear divisor, which is x plus e, for the cubic polynomial p of x equals a times x cubed plus bx squared plus cx plus d, then we're going to always focus on removing terms of x. And by removing, I mean subtracting away multiples of our linear divisor. So then using our polynomials from above, then I'm going to choose a times x squared to multiply our divisor to get a polynomial that will allow me to subtract away my ax cubed. So then I'm counting how many groups of our divisor we're subtracting away. So we've got an ax squared here, and of course they're stored up the top. So then we do our subtraction, and of course the ax cubed is going to disappear, and we've got bx squared minus a times e times x squared. So we've got b minus a times e times x squared. And of course we bring down the cx and the d. Then in our next step, we've got our x plus e, and I need to think about something that multiplies x to get b minus a e times x squared, because that's the next term I want to remove. So clearly that is b minus a times x. Then if we expand that out, we've got b minus ae x squared plus e times b minus aex. And then we continue on till we end up with a remainder that has no x. Now I could keep going on with this, but I don't want the algebra to look too crazy. But hopefully you can decipher a way to make notes that work for you out of this. But it's going to be a lot easier once we start using numbers again. Then across the top, you've written all the terms that you've multiplied x plus b by to subtract away from px. And I should mention that x plus e is your divisor. So you've done all these subtractions and you're left with a remainder, and that's your remainder. I suppose its defining features is that you can't multiply your divisor by anything to become it. And when I say multiply your divisor, don't forget it has to be true for any value of x that you could go in there. Alright, so I do think this is something that I could go round and round in circles on and get you lost in lots of algebra. So I think it's just best that we work through the examples, and that's example 13 today. And in part A today, we're going to divide p of x equal to x cubed plus 2x squared minus x plus 3 by the linear term x minus 2. And I hope you're fine without my color coordination to know which is which in here. Now, after we do our division, they want us to express it with p of x is equal to x minus 2 times some quotient of x plus a remainder. Alright, so let's write out x cubed plus 2x squared minus x plus 3 divided by x minus 2. So we're focusing on the x cubed. So clearly x squared times x minus 2 is equal to x cubed minus 2x squared. Alright, we better put the x squared up the top. So subtracting that away, we obviously get rid of the x cubed, and plus 2 minus minus 2, so we're left with 4x squared minus x plus 3. Alright, so we're focusing on the 4x squared. So 4x times x minus 2 gives me 4x squared minus 8x. Okay, let's put our 4x up here. And subtract that away gives us minus 8 is plus 7. Of course, we bring down that 3. Now focusing on the 7. So 7 times x minus 2 gives me 7x minus 14. Don't forget to put our plus 7 up here. And 3 minus 14 gives me 17. So we're done with our division there. So let's write it out in the way they want us to express it. So we've got x cubed plus 2x squared minus x plus 3 is equal to the divisor times the quotient, which is x squared plus 4x plus 7, and plus the remainder. So that's our answer. Now a pro tip here is you can still check this. People always make mistakes, but people who really understand it know how to check things, all right? So let's expand what we've got here. So we've got x minus 2 times x squared plus 4x plus 7 plus 17. So expanding the brackets on the left. So we get x cubed plus 4x squared plus 7x plus 2x squared minus 8x minus 14. And of course there's still that plus 17. We've got 1x cubed, 4 and minus 2x squared, and 7 minus 8x, and 14 is 3. Whoa, yes. Okay, that worked. So let's go to part B. P of x is equal to 2x cubed minus x squared plus 3x minus 1 this time, and the divisor is x plus 3. So writing that out in long division form. So focusing on our 2x cubed here, we need 2x squared to make x multiply into that. So 2x squared times x plus 3 gives me 2x cubed plus 6x squared. So writing out 2x squared up the top and then subtracting our 2x cubed plus 6x squared away gives us minus 7x squared plus 3x minus 1. So focusing on the minus 7x squared, we need to get minus 7x times x plus 3, because that will give us minus 7x squared minus 21x. And when we subtract that away, it gets rid of the 7x squared. 3 minus 21, so we've got 24x minus 1. Now let's not forget to put our minus 7x up the top here. Alright, so we need 24 times the x this time. We get 24x plus 72. Let's put our 24 up straight away. And minus 1 minus 72 gives me minus 73. So that means we've got 2x cubed minus x squared plus 3x minus 1 is equal to our divisor, x plus 3, times the quotient, 2x squared minus 7x plus 24, minus the remainder, 73. Alright, let's do a pro check. So let's write out our answer, and then we can expand that by multiplying the big bracket by each term in the little bracket. Of course, not forgetting that remainder. So multiplying those factors across the brackets, we got 2x cubed minus 7x squared plus 24x plus 6x squared minus 21x plus 72 minus 73. So there's obviously 1x cubed, and 72 minus 73 is 1. And for our x squareds, we've got a minus 7 plus 6, that gives us minus 1. And we've got 24 minus 21 gives me 3. So we're left with 2x cubed minus x squared plus 3x minus 1. That's lovely when a plan comes together. Also, I think it's worth taking a note about your notes. So lucky for you, the algebra wasn't as long as I was planning to, but I still think it's potentially confusing, and you've got to think about how to express it to make it work for you. But make sure it says basically that we multiply the divisor to eliminate the leading term, x with the biggest power, one at a time. But then once we get to a point where we can't divide by a linear object anymore, we add together all those terms that we've multiplied the divisor by, and that makes the quotient. It is basically the same as the grouped subtraction for long division. Alright, so right about now you should pause that video and do questions 1, 2 and 3 in the new book and questions 3 and 4 in the old book. Also, to go past cubics as a polynomial, i.e. a degree higher than 3, do question 4 in the new book and question 5 in the old book. It might be a good idea that you try those before class, because it's once you're doing those, the cubics will become like a piece of cake. Alright, see you in the summary. So yes, there's a lot of algebra today, but this topic isn't about long algebra just for its own sake. This is going to be vital for factoring and graphing polynomials. But it was also nice to reimagine division. Also, as I said in the last section, this exercise has questions for quartics. Now you can challenge yourself with those, but you really only need cubics for this unit. Alrighty then, so for this lesson, a successful student will know the long division algorithm, be able to carry out the long division algorithm to divide polynomials, and know how to express a polynomial using the quotient, divisor, and remainder. Alright, good luck. We'll see you in class, whether that's in the classroom or the next video. Bye.